Well, this is lecture 31 of Basic Calculus 1. In the last 1 or 2 lectures, we had discussed how to compute area of certain type, that is area between two curves, and then on the left you have a line x equal to a, on the right you have x equal to b. Then such an area can be converted to an integral, definite integral a to b, and then some function, that is f of x minus g of x dx, where f x is the top curve and g x is the down one. So, basing on that we have solved some problems. Today we will be talking about another such application of integrals. It will be volumes of solids, and specifically we will be doing volumes, computing volumes by slicing that. So, there are other methods, we will cover them slowly. Let us look at this particular method, volumes by slicing. So, let us consider a solid whose projections on the x axis give us the points x equal to a and x equal to b, which means within these two planes, x equal to a is a plane now in 3D. It is perpendicular to x axis, that is yz plane, parallel to yz plane, and x equal to b similarly is another parallel plane to yz plane. The volume is lying between these two perpendicular planes. These two are parallel planes, they are perpendicular to x axis. So, by projecting this we get the points, say left end point A and the right end point B. Then what we do? We, as earlier, we will be formulating a Riemann sum for this volume. So, as you see, the volume of the solid will be something like taking a small part of this solid and then looking at it as if it is sliding from A to B. So, say we take, that means it will give rise to some sub interval, say x I minus 1 to x I. So, it will give rise to a partition of the interval a b. So, let us start with a partition of a b into n number of sub intervals. So, the partition points are a itself, which is x 0, and b, which is equal to x n, and in between we choose some other points. So, that x 0 less than x 1 less than x n becomes a partition of the interval a b. Now, in the sub interval x I minus 1 to x I, let us choose a point c I. So, now this solid which is in between, the portion of the solid which is between x I minus 1 to x I, we will approximate that as the area at that point c I is in between that, times the length x I minus x I minus 1. So, that means it will be like a cylindrical type. Instead of taking this exact volume, we will be taking c I, whatever is that area, times this length. So, if that area is something like this and it is moved, it is a cylindrical thing a to b. So, this particular portion will be approximated by such a solid, which we can find out easily. So, it is provided we know how to get the area or the cross sectional area at the point x equal to c I. So, we choose a point c I inside the sub interval x I minus 1 to x I. So, remember all these c I's comprise a set which we call as choice set when you come to integral, introducing the integral, that is for the area below the curve f x and the x axis. Similar way we are doing here, but now instead of f at c I we are taking area at c I. Okay. Then this area of c I or a of c I we write, it is the cross sectional area of the solid at x equal to c I. So, it is somewhere here, it is that cross sectional area. Now, the volume of the slice will be approximated by, it is the portion, that slice is approximated by, as we told, area at c I times the length x I minus 1. Then we form the Riemann sum. So, the volume of the solid is approximately summation I from 1 to n of all these slices. So, each slice has the volume A of Ci times xi minus 1. So, this is an approximation of the volume of the solid. Now, we will declare that this is equal to the volume of the solid when this subintervals lengths approach 0. So, that is our norm of the partition. It is the maximum of all these lengths xi minus 1. So, when that goes to 0, we should get the volume V, which is limit norm p goes to 0 of the Riemann sum summation I from 1 to n area at Ci times xi minus 1. When norm p goes to 0, xi and Ci is between xi and xi minus 1. So, it would look something like approximating at a point Ci, but whichever point Ci we choose, it should not matter. That is the main idea in this limit concept. So, limit norm p goes to 0, and for all possible choice points inside xi minus 1, if this limit exists, then that limit we will be calling as volume of the solid. And now you see it is a Riemann sum where the function is A at Ci, it is not f, it is A at Ci. So, it gives rise to the integral which is A to B, the area as a function of x at a point, the area cross sectional area, and its definite integral from A to B. So, what this approximation and the limit process says, that the volume of the solid can be written as integral A to B, the cross sectional area at any point x on the x axis, that interval A to B obtained from the projection of the solid to the x axis, and then it is integral A of x dx. So, since we are taking slices, we will tell this method that we are computing volume by slicing. So, we will see some problems how do we go about it, but first what is requirement, how do we compute. So, in computing this volume, first thing is we should find a typical cross sectional area perpendicular to the x axis, right. So, first of all we need this point A, we need this point B by projecting orthogonally to x axis within which two perpendicular planes which are both parallel to yz plane, this solid exists, solid remains. So, those 2 points are x equal to A and x equal to B. Then we go for finding the cross sectional area. At any point x, we should be able to express that slice or the cross sectional area as a function of x, and then this should be integrable. A to B A of x dx should be integrable, and that definite integral will be called as the volume. So, let us see how does it proceed. Let us take an example. Say we have a pyramid of 3 units high. So, its height is 3 units, this is 3 units, and it has a square base. So, this is the base we are writing on the right side now, because x axis we are taking this way. So, its base is 3 units on each side. So, that is this is also 3 units, this is also 3 units, okay. And it is starting from the origin, it is the tip of that pyramid. So, the cross section of the pyramid perpendicular to the altitude x. So, x now is the altitude, this way we are looking. This is the base is here. So, altitude, height, everything is measured in this direction. So, now on this base we say that the perpendicular to the altitude. So, perpendicular is a plane now. If the altitude is x, this one is x, then this is the perpendicular. So, that perpendicular, it is x units down from the vertex, is a x units on each side. That is this square, this will be a square where each one of them is x units, right. So, that means it is really going smooth, the pyramid. So, once it is 3, automatically if you correctly draw it, so there will be x on all the sides of this cross sectional area. Now, you want to find the volume of the pyramid. So, to find the volume, what we do? we have the cross sectional area as Ax equal to x square, because it is a square of side x. So, its cross sectional area is x square. So, the pyramid is described for x varying from 0 to 3. Hence, the volume will be integral of 0 to 3 cross sectional area, which is x square dx, and that turns out to be x cubed by 3 evaluated at 0 and 3, that gives 9. So, the main problem is to plot or have a figure which corresponds to the legends or story given in the problem. Once that stage is over, it is just a formula we have to apply. Okay, let us go to example 2. So, here what happens? A curved wedge is cut from a cylinder of radius 3 by 2 planes. So, we have a cylinder, So, imagine it is going this way, standing like this. Okay. On the xy plane, you have its base and it is standing on the xy plane. So, that is what a cylinder will look like, and the downside, it is a circular cylinder. So, it is a circle, that base is a circle of radius 3. So, now such a cylinder is cut by 2 planes. See, one plane is perpendicular to the axis of the cylinder. So, axis of the cylinder is this one. So, to that it is perpendicular, that is, we will take that as the yz plane itself, right. So, this is the z, this is xy plane, because this is z axis we will be taking, the axis of the cylinder. So, we have in the plane xy, there is one plane. Let us choose our x axis and y axis in that base itself. So, that is one plane, and the second plane crosses the first plane at an angle of 45 degree at the center of the cylinder. So, the other plane is this one, this plane. So, that is cutting the cylinder at an angle of 45 degree. So, if you take any straight line on this and any straight line down, so that will be 45 degree. So, which we wrote here 45 degree. Then at the center, so we want to find the volume of the wedge. So, it is one side only we get, the other side we do not get. Okay. So, whatever is really painted, that corresponds to this problem. Okay. So, now the question is, how do we compute? So, let us erase these things, so that this will be clearer. So, now the picture of the wedge looks like this with our choice of the planes. So, now we have the base and x axis there. So, this radius is 3 and it makes the other plane is making 45 degree with this plane. Okay. So, all that we want to see is that we want to compute it by slicing. So, let us take a perpendicular to the x axis, which is parallel to yz plane, and make a slice from this. So, there you find, since it is 45 degree and from the base it is the point x, its height is also x there of the slice. Okay. And what is its length? So, the length will be twice this length. And what is this length? Since it is a circular, the base is a circular base. So, we have the half circle here, of course. Then for any point x here, the y coordinate will be square root of 9 minus x square, right, because x square plus y square equal to 9, its radius is 3. So, this is square root of 9 minus x square. Then the length of this slice, the slice is now a rectangle type. So, it is 2 times square root of 9 minus x square, and the other side is of course x. Therefore, the cross sectional area will be equal to A of x is x into 2 times square root of 9 minus x square, and x has the limits which goes from 0 to 3, right. So, we should have the volume as integral 0 to 3 ax, which is 2x times square root of 9 minus x square and dx. So, that is the integral. Now, we just have to evaluate this integral. So, to evaluate this, we see that you can substitute u equal to 9 minus x square. So, in that case, its differential du will be equal to minus 2x, okay. And when x equal to 0, u is equal to 9, and when x is 3, you get it to be 0. So, that means the integral will be minus, because there is minus 2x here, minus 2x times dx. So, 2x times square root of 9 minus x square. So, that means it is 1 minus integral 9 to 0, it is square root of u du, right. So, that would give u to the power 3 by 2 and then multiplied by 2 by 3, and then 9 to 0 and this minus signs goes away, it is integral from 0 to 9. So, this will be from 0 to 9, or in terms of x you can write same thing as 2 by 3, 9 minus x square to the power 3 by 2, and it is from integral from 0 to 3, right. So, when you substitute 0, you would get to be 9 to the power 3 by 2, and when you substitute 3, that becomes 0. So, that would reach us at 2 by 3, 9 to the power 3 by 2, which is 18. Okay. So, the main problem is here reading the story or the legend of what is given in the problem and translating it to the figure. Once this figure is obtained, we can get immediately this an integral and then compute the integral. Okay. So, let us take another example. Here we have a solid that lies between planes perpendicular to the x axis at x equal to minus 1 and x equal to 1. So, let us take the x axis here. So, at 1 there is a plane, at minus 1 also there is a plane. So, the solid lies between this. So, that means its projection on the x axis yields us 2 points, a equal to minus 1, b equal to 1, that is already given. Okay. Now, the cross sections perpendicular to the x axis between these two planes, that is between a and b, run from the semicircle y equal to minus square root of 1 minus x square to the semicircle y equal to square root of 1 minus x square. So, that means we have a circle really x square plus y square equal to 1, that is what it says, cross sections perpendicular to this. So, that run between these two. So, we have a circle x square plus y square equal to 1. Okay. So, what is that circle? It is cross sections perpendicular to the x axis. So, if you take the cross sections, these planes run from this circle to this. So, that gives the binding of the cross sectional area. Now, you want to find a formula for the area of the cross section of the solid perpendicular to the x axis. So, the cross sectional area is painted here in brown. So, such a cross sectional area we want to find it out. Okay. The solid is such that always it will lie between this circle, that is within this circle you have to take the cross section. So, all that we have to get is it is a circular type, we want to find what is its radius and that would give the answer. So, the radius will be square root of 1 minus x square, because these are the two limits at any point x, right. So, it is the circle x square plus y square equal to 1. So, once you take the cross sectional area, that will have the same radius. Okay. So, once we go up to x here and this one will be in the y. So, y will be square root of 1 minus x square, that is the radius of the circle, which is the cross sectional area. So, once you get its radius, its cross sectional area is pi times r square, which is pi into 1 minus x square. Of course, if you want to find the volume of the solid, then you integrate from -1 to 1 this one, that would give the volume of the solid.